Hello everyone, we're going to talk today about two different types of rates of change. So here's the first question. If a car travels 110 miles in 2 hours, what is its average rate of change? Well, most of you would know that all you have to do is do 110 divided by 2 and you get 55 miles per hour. That is, if we drive 55 miles in an hour, then in 2 hours we'll have driven 110 miles. Second question, if you're driving and you suddenly look at your odometer and your odometer says 60 miles per hour, what kind of rate of change is that? Well, that's an instantaneous rate of change. That is the speed you are going, the rate at which you are going at that very particular time instance. So just remember that average rate of change, we're looking at a period of time. How much does your speed change over a period of time? Instantaneous rate of change is what is your speed at a very specific given point of time.
Liftoff of Ares 1X, testing concepts for the future of new rocket design.
As an example, you have a rocket that's being shot straight up in the air. It's governed by the function f of x equals negative 16x squared plus 128x. What is the average speed between 4 seconds and 7 seconds? Well, to find that out, we would need to know the slope of the secant line between P and Q. I'm going to plug 4 seconds into the equation, and you can see that I did that down at the bottom, and I got, for 4 seconds, I got a speed of 256. A height of 456. For 7 seconds, I got a height of 112. So to know what the average speed was, I would find the slope of that line. I would do 112 minus 256, and then divided by 7 minus 4, and I would get that the average speed of this rocket was negative 48 feet per second over that time interval. Now, how fast is the rocket moving at precisely 4 seconds? Well, in order to answer that question, I'm going to look at it in a series of stages. So first, I'm going to think about the average rate of change from 4 to 6. So I plug in 6 seconds, I plug in 4 seconds, and I find out how far the rocket went. Then I would divide by 2 because it did it in 2 seconds. And I get that the average rate of change was negative 32. Now I'm going to get a little closer to 4 seconds. So I'm going to do from 4 to 5 seconds. Plug in 4, plug in 5, see how far the rocket traveled during that second, and that's negative 16 in 1 second. Then I'm going to get even closer, from 4 to 4.001. Plug both of those in, and you can get that the average rate of change from 4 to 4.001 seconds was only negative 0.016. So what do you think the instantaneous rate of change would be at x equals 4 seconds? And hopefully you'll guess that it's going to be 0 because the rocket is slowing down over that time frame. You should recognize from the classwork that this is a limit process. We are taking the limit as time goes to 0 at 4 seconds. So our quick definition. Average rate of change is a quantity over a period of time. Average rate of change of a quantity over a period of time is the amount of change divided by the time required. It's nothing more than a slope. It's the change in y over the change in x. And you know this intuitively. If I tell you that you traveled 250 miles and it took you 7 hours to do it, you would do 250 divided by 7 and you get 35.7. So average rate of change is just a slope. It's the slope of the secant line that connects the beginning and the end of the time period. And you find it by using the slope formula. Now what about this case? We want to find in words, or we want to find the time at exactly the 5th hour. Well, over a 7-hour trip, sometimes you're going faster, sometimes you're going slower. You may average 35.7, but at every point along the way, you're probably doing something else. So to find that, we have to find an instantaneous velocity at a point. It's the slope of the tangent line at that point. Now once again, hopefully you recognize from our classwork that this is the derivative. Now, derivatives are used for many different situations, and the one we're going to use it a lot in class is the free fall position function, which is given by this equation. So s is height or position, g is the gravity, v sub 0 is the initial velocity, and s sub 0 is the initial height, and of course t is time. So you're going to want to write that down so that you can remember it. As long as we're on Earth, we always use gravity to be negative 32 feet per second. This is not physics class. We're not going to do things in meters. We're going to stick with feet per second. So we're going to use negative 32 feet per second for gravity, so 1/2 of that would be negative 16t squared. That's our position function at the top. The velocity function is the first derivative. So I just use the power rule to take the derivative of the position function. Then the acceleration function is the second derivative. So I took the derivative of the derivative, and that gives me my acceleration, which you'll notice is simply gravity. Gravity is negative 32. Gravity is an acceleration. So here's an example problem that we're going to do together. I want to find the average velocity over this time interval. Alright, hold on a second, let me go back again. And so let me get my pens to working here. Okay, so we want to find the average velocity. So to do this, I'm going to plug in 3/4 of a second into my position. So it's going to be negative 16 times 3/4 squared plus 32 times 3/4. That's going to give me negative 9 plus 24, which is 15. So the height at 3/4 of a second is 15. Then I'm going to do the same thing for 5/4. So if I plug that in, 5/4 squared plus 32 times 5/4, that's going to give me negative 25 plus 40, which is going to equal also 15. So then my velocity is going to be 15 minus 15. It was at 15 and it's back at 15 over the time frame it took to do that. So it traveled 0 height. Change in height was 0 in 1/2 a second. So my average rate of change then is 0. This is the average velocity. Second question, what's the instantaneous velocity? Well, the instantaneous velocity is the derivative. So I'm going to take the velocity, which is the derivative of s. Using the power rule, the velocity is negative 32t plus 32. So then the velocity at 3/4 of a second would be negative 32 times 3/4 plus 32. Well, that's going to be negative 24 plus 32, so that's 8. And then I can do the same thing at 5/4, and that would be negative 32 times 5/4 plus 32, and that one then is going to be negative 8. So at time, alright, so then this one is also negative 8, and so at 3/4 of a second, the ball is going up at 8 feet per second, and at 5/4 it's coming down at negative 8 feet per second. Now, how many seconds will it take the stone to reach its highest point? To do this, you have to imagine, so we're starting on the ground, the stone's going up, and it's going down again, and we want to know when will it reach the highest point. Well, to figure that out, we have to realize that at this highest point, the velocity is 0. So remember from our previous slide, the velocity was the derivative, negative 32t plus 32. If we're trying to find the velocity, we're trying to find the time it takes to reach the top. The velocity is 0 at the top. So set it equal to 0 and solve. So I get negative 32t equals negative 32, so t equals 1. So it takes 1 second for it to reach its highest point. How high will the stone actually go? Well, that's our height function. So the height is s equals negative 16t squared plus 32t. Now, just a minute ago, we figured out that t equals 1 is when the stone is at the top. So all I'm going to do then is I'm just going to plug in 1 second, and that's going to give me the height at the top, and that winds up being 16 feet. So it's going to take 1 second for this stone to reach the top, which is 16 feet. How many seconds will it take the stone to reach the ground? Well, there's 2 ways. Now, if we use the fact that we know it took 1 second to get to the top, so 1 second to get there, intuitively, you know it would take 2 seconds to come back down again. An algebraic approach would be, well, if this formula is position, which in this case is the height, what's the height of the ground? Well, the height of the ground is 0. So if I set this equation equal to 0 and I solve it, I'm going to factor out a negative 16t, which leaves me t minus 2 equals 0. And I solve that, I get t equals 0 and t equals 2. So 2 seconds to reach the ground. So here's a question I'd like for you to try and do this using the methods that we just talked about. See if you can figure out the answers to this question on your own, and we'll talk about it in class tomorrow. So good luck, and I will see you tomorrow.